Hello and welcome to the 6th lecture. So we are going to be talking about 2.6, limits at infinity and horizontal asymptotes. Okay, so let's start with an example. Consider this function. As always, we're going to try and visualize this guy. So, in this case, simply graph it. So, when x equals 0, we're at minus 1, right? When x is plus or minus 1, we're at 0. And so we're going to do something like this with this function. Okay. This is always going to be less than 1, right? Because the thing on the top is always less than the thing on the bottom. And so we're always less than 1. But as we let x get bigger and bigger and bigger, we can see this is actually going to tend closer and closer to 1. Right? So if you can't see this straight away, and plenty of you won't be able to see this straight away, what will you do? Well, just put large numbers in for x. So if we put 10 in for x, we're going to have 100 minus 1, which is 99, over 100 plus 1, which is 101, right? And that's a number very close to 1. If we put 1,000 in, then we're going to have 1,000,000 minus 1 over 1,000,000 plus 1, a number even closer to 1, right? So you can kind of somewhat easily see that as x gets bigger and bigger and bigger, this thing is getting closer and closer to 1, and this is the shape around 0. So that's our guy, okay? And what this thing is exhibiting is something called a horizontal asymptote. So let's define it. So definition. Okay, so I'm going to write it in the language of maths, and then we're going to write it in words. And the thing that's really going to clarify it is the picture. Okay, so first, this is what we write in the language of maths. Let me do it. Let me do it well. In the language of maths, what we have with the limit as x goes to infinity, f of x is equal to L. And what does that mean? So, in words, this means we can get, or we can force f to be as close to L as we like by restricting x to be sufficiently large. Okay, let's draw the picture. So we have some graph, we have some function on the graph, and we have some value L, some limit L. And what the function does for small x, we don't really care, but what we do have happening is that the function tends closer and closer to the value L as we get further and further to the right. So I'm going to overlay my words here. And what would have been smart would have been to choose different colors. Don't worry about that now. So if we take any strip around the value L, arbitrarily thin, we can guarantee that f of x is inside this thin strip around L so long as we are far enough to the right. So there exists some number, let's say m, such that for every x bigger than m, we are going to be trapped within this thin strip. Okay? And this is very similar to what we've seen before. So previously, when we talked about a limit, we would have some function. Here would be L. And the function would be whatever, something like this. Okay? And what we were doing previously is we were saying we could trap the value of the function to be arbitrarily close to a thin strip around L by restricting the values of x to be around a very small neighborhood of A. Okay? Yeah. And this is the same game, except now we're not restricting the values of x to be sufficiently close to a small neighborhood of A. We are restricting the values of x to be sufficiently large, but we have the right to choose how large they are, right? We have the right to choose this point where we only guarantee that f of x is within this thin strip for x bigger than this point, and we have the right to choose it, right? And it can be as big as you like. So if you want to get within 1 over 100 trillion, then you can do it perhaps by taking m to be 100 billion trillion zillion, whatever. Doesn't matter how big an m you need, but what you have to do is be able to ensure that you can get within any thickness of this strip by going far enough to the right. And for every x bigger than that point you decide on, it will be within that level of accuracy. Whereas in this game, or in this definition of a limit, when you're limited at a point, we got within any accuracy by restricting the values to be sufficiently close to A but not equal to A. And we had the right to choose this tiny interval. We have the right to choose this point where we only guarantee for all x bigger than this point. So it's very much the same kind of concept, but now the restriction on the x is different, what we are. The thing that we can guarantee is true for all x. It's now a different thing. It's for all x sufficiently large. So informally, we say it's a limit at infinity because if it's true for all things sufficiently large, then it's true at infinity, because what would it mean to be getting towards infinity? It means being bigger than any big number, right? So that's why we say it's the limit at infinity, and it's a little bit of a kind of abuse of language, because as you know, you never get any closer to infinity, right? So whether you are here at m, which is whatever, a billion, or at some other number, 100 trillion zillion, you're still infinity away from infinity. So don't get hung up on this. This is just language. What we mean by this, limit as x goes to infinity, is that we can guarantee arbitrarily small error for all large enough x, and we have the right to choose where this is true from. So if you remember my analogy of my metaphor of when you do this, it's like signing a contract. When you say a limit is true, you sign a contract. You guarantee whatever accuracies your boss asks from you, but you have the right to insist on whatever. In this case, you have the right to insist on whatever tiny neighborhood around A, not including A. In the case of the limit at infinity, you have the right to insist on whatever m, where it's only true for x bigger than m. All right, so think about this for a little bit. If you're comfortable with the concept of limit, you'll be comfortable with this concept of limit at infinity. It's a very similar thing, okay? And this is the main topic we're going to discuss today. We're going to learn about these limits at infinity. So let's think about this guy. Is it the case that the limit as x goes to infinity of this guy, x squared minus 1 over x squared plus 1, does this thing exist? And what I hope this kind of picture and this kind of explanation kind of gives you the impression is that, yes, this limit does exist, and this limit is 1. And later we'll learn how to precisely figure that out. But that is why we start with this example. This is an example of something that is a horizontal asymptote. Okay? All right. So this is called a horizontal asymptote. So if f has limit as x goes to infinity, f of x equals L, then y equals L is the horizontal asymptote. So this horizontal line at L is the horizontal asymptote. Okay. All right, let's do a very simple example. What if we have f of x equals 1 over x? So, do we have that the limit as x goes to infinity, f of x exists, is some limit? And what I hope you guys do when you see a function like this is you try and picture what it looks like. So if we carve in some space, not much space here, if we try and visualize 1 over x, this is one of the elementary functions that you need to be able to visualize pretty quickly. And what do? We see something like this, and we see something like this. So I said this in class and also in these video lectures. We will be building examples from elementary functions, and they are, let's make a small list. What are they? They are polynomials, rational functions, trig functions, inverse trigs, log, exponential, root functions, what you guys might call radicals. All of these things you should have a reasonable idea of. Not that you can visualize every polynomial, but every simple polynomial, x squared, x to the 3, x to the 4, you should be happy with. Every simple rational function like 1 over x squared, 1 over x to the 3. All of these guys, the faster you have them clear in your head such that when you see it written down, you have the picture, the easier this stuff gets. Because that's what you're going to have to do. You need to turn this stuff into pictures, develop this muscle. And the way you do it is that whenever you see some function that you can't visualize, you stop whatever the rest of the problem is, and you just figure it out. And you don't figure it out by typing it into Wolfram Alpha and looking at the graph. You figure it out by just messing around with it, just by putting, at worst you know how to do it. You can plot values and stick them all together. But hopefully you can just do it without that. You can just ask yourself what's happening as x tends to this, x tends to that. So in this example, as x tends to 0, we should see that if it goes to 0 from the right-hand side, it's 1 over a very small positive number, so positive infinity. And as x goes to positive infinity, it's going down to 0, right? So if you're not in a position to do that now, and plenty of you won't be, then get to that position as quickly as possible. It's going to make this whole thing a lot easier and a lot more successful for you. Okay, back to this. So we have this example. We know it looks like this. So do we have this? The answer is yes. And we know that the limit as x goes to positive infinity f of x is going to be 0, because if you take any thickness around the horizontal asymptote y equals 0, you can certainly guarantee you're within that thickness, right? Take your favorite tiny number. Let's say the tiny number you choose is 0.001, right? Then how can you guarantee that 1 over x is within that range, right? So if you just take m to be 1 over 0.001, then you will be fine, right? Because if x is bigger than this number, then 1 over x will be less than this, right? And you're there. So, and x is bigger than m, then 1 over x is less than 1 over m, which is the number you're interested in. So in this case, it's very easy to see that you can get within any thickness of 0 that you want. Okay. All right, so having done this guy, let's consider this thing, the limit as we go to minus infinity f of x, okay, for an arbitrary f. So definition. This is exactly the same as the limit when x goes to infinity, except now we're going towards the left instead of towards the right, okay? So instead of having this picture, I would draw the picture going towards negative infinity. So in words, it means we can guarantee that f is with an arbitrarily small error of L so long as x is sufficiently negative, which means it is less than any negative number you want. So it's less than whatever, minus a billion, minus a trillion. You have the right to choose how far to the left, how far to the negative you are, how close you are to negative infinity, okay? So defined analogously, oops. And I apologize for massacring the spelling of these words. Analogous. I have no idea how this is spelled, but you know the word I'm trying to say. So this is defined analogously. We're going to the left instead of to the right. And we can also ask questions about the limit to negative infinity. So what about the limit x goes to negative infinity, 1 over x? Same kind of reasoning. You should be able to figure out that this is just going to be 0 as well. Cool. So that is kind of an introduction. Let's take some more tricky examples, or slightly more tricky examples. Let's look at this guy. So this is example 3. The limit as x goes to infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. Okay, how should we try and figure this out? Well, as a first approximation of the truth, just to get some intuition, this is something you can do. So you can look at this quantity here, or this function, 3x squared minus x minus 2, and for very large x, this is really a lot like 3x squared. So if you take this quantity divided by 3x squared, you'll find that the limit tends to 1, which means that even though this is always less than 3x squared, the percentage difference gets arbitrarily close to 1, or the percentage, this is arbitrarily close to the full percentage value of this. It's a very awkward way to express it. What I mean is that whatever this number is, you can guarantee that this thing is 99% of this, so long as x is large enough. That's what I mean. Yeah? Just because if you look at this, 3x squared minus x minus 2 over 3x squared, and we do the algebra, we're going to have 1 minus 1 over 3x minus 2 over 3x squared, right? And that thing is arbitrarily close to 1, right? So you can get this thing to be as close to the full value of this thing as you like, 99.9% of it, as you let x tend towards infinity. So morally, it looks like this for very large x. And the same is true for this other function, 5x squared plus 4x plus 1. Morally, it's an awful lot like just 5x squared. Again, for large x. So the ratio of these two numbers, or these two functions, as x gets larger and larger and larger, we could expect it to be something like 3x squared over 5x squared, which is 3 over 5, right? And that is like the rough, quick way to get an answer. So the leading order term on the top here is x squared. Even though this is growing or getting more and more negative, it's just a tiny, tiny perturbation of 3x squared as x gets bigger and bigger. Same is true here. Even though 4x is growing towards infinity, this is so much faster growing that we kind of doesn't see it for large enough x, right? So when we consider this quotient, really all we care about is the quotient of the 3x squared over the 5x squared, which is 3 over 5. So we could have a pretty good guess that the limit as x goes to infinity is 3 over 5. And that's the rough kind of quick way to get some idea what the answer could be. But we want to be more precise because sometimes our intuition is wrong. Sometimes we don't have an intuition, and we have this tool, we have this language that allows us to express these things more precisely and really see if we're correct, right? And as you do more maths, you'll find that many times the more you do maths, the more your intuition will be correct. But it won't always be correct. And the way it gets more correct is that you'll have instances where your intuition is not giving you a clear answer, or is giving you a wrong answer, and you'll find that out by expressing your ideas carefully in the language, and then you'll see what the actual truth is. That's the power of this. It allows you to carefully break down what your thoughts are, express them, and see if they're correct. Okay? All right, so let's do this. Okay, so we were looking at this guy. Okay, and we're trying to take the limit as x tends to infinity, and we thought that the answer was 3 over 5, right? But let's try and make sure, let's try and nail this down as completely as we can. So what can we do with this expression? Well, the natural thing to do would be to factor out the x squared from the top and the bottom, because it's a leading order term. And if we do that, we're going to have x squared 3 minus x, minus 1 over x minus 2 over x squared, right? And on the bottom, we're going to have x squared 5 plus 4 over x plus 1 over x squared. And we're taking the limit as x tends to infinity, so x is definitely not 0, so we can cancel it from top and bottom. 3 minus 1 over x minus 2 over x squared. And on the bottom we have 5 minus 4 over x plus 1 over x squared. Now, we know that the limit of the top, well actually let's do the bottom first. We know that the limit of the bottom is just going to be 5, right? For sure that's true. We can just break it up, some of these different limits. This has got limit 0, it's got limit 0, so the limit is 5. And the same is true that the limit of the top is going to be 3, right? And this is the quotient of two functions. So if we take this, call this thing star, so the limit as x goes to infinity of star is equal to the limit of this quotient, right? And by the quotient rule for limits, when we have the limit, let me write it down here, of f over g, this was equal to the quotient of the limits, so long as the bottom limit is non-zero. This is g. Yeah? If the limit as x tends to 0 of g of x is not equal to 0, right? This is the quotient rule for limits. There we go. This we know. Yeah? So, when we take the limit, we have this would be f and this would be g. And we know that both these limits exist, and we know that the bottom limit is non-zero. So we can apply the quotient rule, and this is the same as the limit as x tends to 0 of the top function over the bottom function. I'm doing this really carefully, really nailing it down, just to show you how to do this, because you will have to do this yourselves when you do free response questions in the exam. Okay? So just to nail it down by quotient rule. Because as you might know, but perhaps you don't know, the exams we give are a mixture of multiple choice and free response. And the multiple choice, obviously it's just multiple choice, you need the right answer. And in that case, for a question like this, you could use this kind of reasoning I did very quickly to get the answers 3 over 5. And the more questions of this kind you do, the more comfortable you are about why it's 3 over 5. If you figure out this in detail a number of times, you will quickly be able to read off the answer to these questions. And you won't get them wrong. This is quite straightforward if you practice it. Yeah? However, if this is a free response question you should think of as writing a little essay in the language of math where you explain your reasoning as if you're kind of a lawyer arguing a case in court, nailing it down, showing that there's no gap in your reasoning, that you understand everything, that every step you make in the argument is valid, right? So you should bear in mind that the examiner is skeptical and is looking for things which you do that you can't justify or you don't know why it's true. So in that case, it is don't argue the way I did down here. Don't say morally this is like 3x squared over 5x squared. Even though that's correct, that is not the mathematical complete explanation. Do this algebra, yeah? Point out that you have these two functions, both of which have a limit, right? And then mention the quotient rule, and then that's it. Then you can't possibly be criticized for not understanding why this is true. And I appreciate that many of you will think, okay, this seems like an overkill here, and I agree. But this is not. The point of these response questions is to give you practice and teach you and force you to learn how to express yourself in this language clearly and how to go through this process of carefully expressing all your thoughts and explaining why all these reasonings, all these steps are valid. And that process is the very powerful process because as I said, your intuition isn't going to be always available to you, isn't always going to give you the right answer. And we'll see examples coming up shortly where there isn't an obvious answer. Well, you probably won't see one, but we can do this kind of thing. We can use the powerful language where we are learning and have already learned a fair bit to analyze it and really understand what's going on. Okay, so we have the answer. This is the limit, and this is the kind of thing you need to write in a free response question. So write like this. And consider it really like an essay. So don't just write a kind of chaos of things squaring all around and then hope that you're going to get points for everything that's correct in the mixture of all the things you write down. That might have been how you were graded in high school, but that's not what we're doing here. This is a precise language. This is the power and the beauty of it. It's a very precise language. You can express yourself very, very precisely, and that's what you need to do. So if you do free response and you write a whole bunch of stuff that is wrong as well as stuff that is right, you will lose points. So don't think of this as like firing a shotgun. Think of everything you can possibly think of connected to this and write it all down. Write an essay. It's an essay in the language of maths. Be clear and concise and write the things that you know. And if you don't actually know if you can't use language of maths, use ordinary language, but write down your thoughts. Write down and as clearly as you can. But you should be able to use the language of maths. That's what we're trying to teach you. You should have learned how to do it from doing all the homeworks, the examples, and watching what I do. All right, so write this in the free response. Write like this in the free response questions. All right, let's do some more examples. Let's do this one, example 4. Limit as x goes to infinity of 2x squared plus 1 over 3x minus 5. Okay. Solution. So the quick and rough way to do this, you say, okay, what is this like for very large x? Well, this thing on the top for very large x is an awful lot like just square root of 2x squared. So is like square root of 2x squared, which is actually just square root of 2 mod x for very large x. And on the bottom, 3x minus 5 is like just 3x for very large x. And then you can guess the answer, right? So both of these things are growing at the same rate. So we would guess, let's call this thing star, is just equal to root 2 over 3, and you would be right. Well, you would be right. And if you want to nail this down completely, what would you do? You would factor out the x squared from inside here. So more completely. Do some algebra. We have square root of 2x squared plus 1 over 3x minus 5. We pull out this, I'm going to have this, so value of x, just 2 plus 1 over x squared over, let's pull out x from this, 3 minus 5 over x. And then it's clear, right? So if x is positive, going towards infinity, we cancel these two. We take the limit, so let's just write that. As x tends to infinity, we know the limit of the top. It's just going to be root 2. And we know the limit of the bottom will just be 3. For large x. Okay. And so that is going to be the answer. And this time I didn't write down the quotient rule and everything else, but that's what you should do if you're doing a free response. Yeah? We could also consider this question. What about the limit as x goes to minus infinity of this function? And the same kind of stuff we're doing over there makes it kind of clear, because when x tends towards negative infinity, then what this equality here is no longer true, right? Because if x is negative, then absolute value of x is positive, but this is still negative, right? So the whole expression, this x over is mod x over x will now be minus 1, right? So if x goes to negative infinity, then this thing we can't just cancel like this, right? If x goes to negative infinity, then when we have mod x over x, then that is equal to negative 1. So we get just minus root 2 over 3. And that's it. Cool. All right, so other examples. Okay, let us consider this example. What about if we do f of x is equal to sine of x? Do we have a limit as x tends to infinity? So does limit as x tends to infinity f of x exist? And the answer is no. Definitely not. Because we know what sine looks like, right? It looks like this. And there is no value of L where we can trap a function within a thin strip around L for all sufficiently large x. That's wildly false, right? There's no way to do that because it's always going to oscillate between -1 and 1. So it's completely failing to be trapped within any limit at all. So no, from the picture. Yeah. So what about if we do this? What about f of x equals, say, sine of x over square root of x? Well, then the answer is yes, because sine is oscillating between -1 and 1, right? But this root x is getting bigger and bigger and bigger. So it's forcing the oscillations to be smaller and smaller and smaller. So in that case, the picture, let me superimpose it to this. Actually, I need to get rid of all of this stuff. In that case, the picture looks like this, right? And we can trap it to be closer and closer to 0. Yes. That's the limit. As x goes to infinity, f of x equals 0, as we can clearly see. All right, let's consider a couple more examples. Can I fit another one in here? No. All right. Let's erase the board and do some more examples. Okay. This is example 5. This guy is very cool. So let's consider this limit. The limit as x tends to infinity of square root of x squared plus 1 minus x. Cool. So this guy is very interesting because we don't have an obvious intuition what the answer is, right? This is tending to infinity, this is also tending to infinity. It's not clear what this will be, right? And if I hadn't done many of these types of questions, I would have no idea. Right? I just wouldn't know. However, we have the language of math. We can analyze this, right? Solution. So we look at this expression, x squared plus 1 minus x. And what we don't want to deal with is square roots, right? Because we just don't like them. So you guys, or you people all know this, right? If we do a minus b times a plus b we get a squared minus b squared, right? Everybody's happy with that. And that's a good way to kill square roots. So we multiply it by something sometimes we call this a conjugate. If you haven't been calling it the conjugate, it doesn't matter, it's just words. Yeah? So what do? We want to try and kill this using this identity. So what if we try and multiply it by this a plus b? So in this case, a is this thing and this thing is b. So if we multiply it by something like square root of x squared plus 1 plus x, then that would kill this, but obviously we want the same quantity, so we're going to also divide by this. Otherwise, the whole expression is different, right? So this thing is just 1, so we're just multiplying by 1, but on the top line, we now have this nice algebraic simplification. So using this now is going to be a squared, so we're going to have x squared plus 1, and then this will be minus x squared, and then underneath this expression, square root of x squared plus 1. And here we have x. Yeah? Cool. And obviously the x squareds cancel, so put it here, we just have 1 over square root of x squared plus 1 plus x. And now this is easy to understand because as x tends to infinity, the stuff on the bottom is going arbitrarily large, right? So let's call this thing star. So star is equal to the limit as x tends to infinity of this quantity over here, 1 over square root of x squared plus 1 plus x, right? And that thing is equal to 0. Cool. So we can do this example too. All right, let's do, actually I have it in my head, let's do the next example. Let's change colors. So, okay, example. Let's consider this function. F of x is equal to arctangent of 1 over x minus 2. Okay? And our question is the following. Does the limit as x goes to 2 plus f of x exist? And if so, what is it? Okay, solution. So we have this function which is composed of these two other functions, and our first thing we want to do is try and get some idea what it's like. So first let's try and understand this 1 over x minus 2. Yeah? So let's use space better. We clearly have something going on at 2, right? So at 2, as we approach 2 from the right-hand side, then we have on the bottom a very small positive number, right? And on the top we have 1, so this thing is going to be blowing up like this. And as we approach 2 from the left-hand side, for numbers less than 2, then this on the bottom is a very small negative number, so then it's going to look like this, right? So this is what 1 over x minus 2 looks like. And if you think about it for a second, it's just the graph of 1 over x just shifted by 2 in that direction. Okay. Arctan, we know what it is, right? So let's put it here. So arctan, change colors. So arctan, what does it look like? We know it well. It looks like this. Right? And here we are at pi over 2, and here we are at minus pi over 2. And as we go towards infinity, we get closer and closer to pi over 2. So what are we doing in this question? We're taking the limit as x goes to 2 from the right-hand side. So let's take some arbitrary x very, very close to 2, but to the right of 2. Then 1 over x sends it way up here towards infinity. Yeah? And that's the thing that we plug into arctan. So then we are way over here towards infinity, and this is where we're going to plug in this 1 over x minus 2, because it's very, very close to infinity. And if we plug that into arctan, we see we're getting very close to pi over 2. Yeah? And the closer we go to 2, the further we are towards infinity, the further to the right we are on this graph here, arctan, the closer we are to pi over 2, right? Which is exactly saying that this limit will be equal to just pi over 2. So, okay, and what are we doing here? Well, we are using the fact that if we have functions, continuous functions, and we compose them, then we can figure out the limit just by having the fact that the limit of f composed with g is f acting, start again. The limit as x approaches a of f composed with g is f of the limit as x approaches a of g, right? That's what we learned previously. I don't want to write it down because I fear it's going to look more confusing. But if you look back, that is what we talked about in the lecture on continuity. And the way we figured it out was we drew a couple of graphs, and we just saw what happened to our x. It went through the first inner function and then into the outer function, and we just followed the consequences of the hypothesis that limit as x approaches a of g exists, and that the limit, and that limit will say L, and the limit as x approaches L of f also exists, right? Yeah. And what we're doing here is like the explanation which we did in that theorem, but we're doing it individually for these functions. So to say it a different way, we're using the method which we use to understand that theorem for the specific case. Rather than applying the theorem, we're using the method to understand what this thing is. And that's really a valid thing to do. Once you understand a theorem, then it should be, it is natural. It's just a few pitches. And understanding it, understanding why it's true, means that you can use the same reasoning to figure out individual examples rather than remember some fact and apply it. And that I'd rather you did that. I'd rather you remembered why something is true and figured out some specific example because of why something is true rather than remember a fact and apply it. But those of you who are on the ball or are very diligent will recognize the reasoning here. It's exactly the same reasoning we used when we did this theorem about composing functions and taking the limit. And there's a reason, because we're composing functions and taking a limit, right? All right, so this is our answer. We see it from the pictures, and we are quite happy with this. Okay, let's talk about, I think I've covered all the examples I want to of this. Yeah, I believe so. Okay, maybe do one more example. Sorry, I'm just going to leave this session here. Let's do another example. What about this limit? The limit as x tends to infinity, e to the 1 over x. It's a similar game. It's the composition of two functions, right? There's e to the x function, and the 1 over x function, right? So if we draw the graph, 1 over x is looking like this, positive x, yeah? And e to the x, it's blowing up, but we are considering, so this is 1 over x, but we are considering it closer and closer to 0, right? Because as x tends to infinity, 1 over x tends to 0. So the graph of the exponential function is like this, right? This is e to the x, but we only care about it very close to 0. So let's track what happens as we take x towards infinity. So we take x towards infinity, so let's follow the path of our x in this composed function journey. So as we take x towards infinity, right, 1 over x takes it towards 0. So this will be where we are. We're like 1 over x, really close to 0. And then we plug that in to the graph of e to the x. Yeah? So where are we going to end up? We're going to end up closer and closer to this, closer and closer to e to the 0, which is 1. Right? So this is equal to 1 because of the pitches. And again, we're doing this composition of functions and limits of composition of functions, but we're breaking it down into the pitches and applying the method. All right, cool. All right, now we have a final concept to discuss, and that's infinite limits at infinity. So okay, so we write the limit as x tends to infinity, f of x is equal to infinity. And what we mean by that? We mean the following. So let me write in words. Means we can force x to be as large as we want by taking or by insisting that x is sufficiently large. Insisting that x is sufficiently large. Again, when we write in the language of words, this is very cumbersome and lengthy. Picture, of course, is the reality of the situation. And what does it mean? It means that if you give me your favorite big number, whatever it is, this number L, I can guarantee you that the function is bigger than L so long as you give me the right to take sufficiently large x. So I have the right to say, okay, I can promise you that f of x is bigger than this number L that you're keen on, so long as we take x bigger than some particular value, right? So the function could be doing any kind of stuff, but I guarantee you we are bigger than L so long as I have the right to choose where we consider all the x's from what point onwards to the right. Yeah? And that is true for any L. And if that's true for any L, that means your function is bigger than any big number you might want, so long as you are sufficiently far to the right. For all x sufficiently large, far to the right, emphasize for all x, not just some, but for all of them, then that is like saying we're getting towards infinity if you allow some kind of looseness in language. If you accept that being as big as you like is getting towards infinity, that's what we mean by towards infinity, then that's like saying the limit as x tends towards infinity is infinity. So it's infinite limits at infinity. Again, it's nothing massively different than what we did before. So we discussed infinite limits before as x tends towards some point, but now we're doing infinite limits as x goes towards infinity. Another thing to mention, even though we write that the limit is something, we don't say that the limit exists, because when we say the limit exists, we only mean as a number. So let's change colors. So example. F of x equals x to the 3, then the limit as x tends to infinity, f of x is infinity. So even though we write this answer, we say that the limit does not exist because we mean it has to exist as a number. Don't get hung up on this. This is nothing deep. It's just a convention. It's just a convention. Yeah? And there's a reason for this convention, but it's not an important thing. Yeah? There is an answer to the limit is infinity, but we nevertheless say it doesn't exist because when we say it exists, we mean exists as a number. Okay, and we can also figure out that the limit as x goes to negative infinity, f of x is negative infinity. Yeah? Not too hard. Okay, so final thing to talk about. So, this is an example. Let's consider this limit as x goes to infinity of x squared minus x. Okay, so what you should be thinking is, okay, both of these guys are going to infinity, but this guy is going faster, so I think the answer is infinity. And in fact, a bit of algebra clarifies this, because what do? We go, okay, x squared minus x, that's the same as x minus 1, and both of those guys are going towards infinity, and we're producting these two very big positive numbers, so it's even getting even bigger. So for sure, this is going to infinity. So the limit as x goes to infinity, x squared minus x equals the limit as x goes to infinity, x minus 1, which is equal to infinity. Okay. There is a totally wrong way to do this, which we sometimes see. So this is the wrong way. So sometimes we will be marking a free response or something, and we'll see some argument or some reasoning like this. A student will go, okay, this is the limit of the difference of two functions. And I know the limit of each one of these. I know the limit of x squared at infinity is infinity, and I know the limit of x at infinity is infinity. So I'm going to break it up using the limit laws. So use the limit laws. They claim you can use the limit laws, and you can write this. And then they write, okay, well then that's infinity minus infinity, which is 0. Very bad. Because the answer is definitely not 0. But formally, this looks kind of okay, right? This looks kind of reasonable. What is unreasonable is the fact that they use the limit laws when the limit was infinity, because the limit laws are only when the limit exists. It doesn't exist when it's infinity. And that's the reason, that's one of the linguistic conventions, that's one of the reasons for the linguistic convention of only saying the limit exists when it exists as a number. Because you can't do arithmetic with infinity. Infinity isn't a number. You can't apply these limit laws like this. You certainly, you just get into utter nonsense if you do. And another classic thing about this, which is exactly what I'm trying to avoid any one of you, another classic trap in this false answer, which is a trap I'm trying to prevent any of you from falling into, is that anyone who argues this like this is not thinking about the meaning of these things. This is a thing that this is in the language of math. This describes some function, something, right? And in arguing this way, if you argued this way, you wouldn't be thinking about the meaning. You would be thinking about some rule that you remembered, and you'd be trying to apply a rule, right? And you're almost right. I mean, it looks kind of convincing on first glance, because there is a rule about taking the limit of difference of two functions and breaking it up. But you can't apply it in this case because of the fact that the limit doesn't exist when it's infinity. But you're very close to having the right rule, right? This is an easy mistake to make if you're trying to remember things. If you're trying to remember rules and apply rules, then this kind of thing is easy to do. No? And as I said in my introductory welcome to the class video, a lot of people, and me included, when they were in high school, were taught maths as just, here's a sequence of steps to do, a bunch of rules to learn, follow the steps, don't make a mistake, and there's your answer. And that's what we've got to break you out of. You have to not use your memory, not memorize things, not memorize rules. You have to think about what things mean all the time. If you do that, then you won't make this mistake, because you'll be thinking, okay, x squared minus x, I have some idea what that looks like. The x squared is killing the x. They're both going to infinity, but x squared is getting way bigger, way faster. In fact, I could do some algebra and I see it's the product of two very big numbers. So for sure it's going to infinity. Therefore, before I do any kind of writing some maths, manipulating some symbols, I have a pretty good idea what's going on. And if you wrote something like this, you'd go, wait, that can't be right. There must be a problem here. And you think, okay, yeah, this is the problem. I can't do this. I certainly can't treat infinity like a number. I can't subtract it from itself. And that's how you wouldn't fall into this trap. So it's a simple example, and you know, once you see it, you might think, okay, I would never make that mistake. But trust me, I have graded hundreds and hundreds of exams with mistakes very similar to this. Clearly, people had been studying, but just not studying the right way, not doing the right thing, not thinking about the meaning of this language, not visualizing it, learning rules. Don't learn rules, don't memorize stuff, think about the meaning, turn the language into pictures at every stage. That's the real thing, the pictures are the math, and you won't be falling into this trap. Okay, that's it for today. Have a great day. I will see the Friday group on Friday.